George is fine.
George from LBL in Stanford. And the title of his talk is Photonics-Based Resource Disaggregation for HPC.
And DW, long title, I know. Also, many collaborators I'd like to thank from Columbia, LBL, and New Mexico State University. So when I put together this first slide, I didn't realize how many talks about disaggregation there would be. So maybe we don't need that much convincing. However, one difference with my talk is I'd like to give you guys the HPC perspective, and I'm talking about the scientific kind of workloads that we run at NERSC. So I'm talking about open science workloads, a lot of linear algebra, and like density functional theory, physics simulations, and so on, which means that these systems run workloads, many kinds of workloads, many requirements, and it's hard to predict the kind of workloads too. That said, we did sample NERSC Perl Matter, the most recent system, and this is a plot for specifically CPU nodes, and we did notice that memory capacity, which is what's shown here, is underutilized. So CPU nodes have half a terabyte of memory, and 50% of that is used, 50% or less is used 64% of the time. So there's a lot of capacity that goes unused just because there are few important workloads that use it, but those workloads are infrequent. So I'm going to make the bold claim that I don't have time to support, but we have papers about it. We have a couple of papers that, based on the analysis of these systems and what we've profiled as workloads, intra-rack resource disaggregation is enough to get most of the benefit. And what I mean by that is sharing resources only within the rack and not even across racks, although we could expand to that, not even across the system. So to visualize the concept is now we have a rack that's made of 4 nodes and they all look the same, and we want to go to a situation where the rack can pull and compose and give different applications the resources they want. If you want pointers to those papers, we have to do it, but again, this is dependent on the workloads that we're experiencing at NERSC, the open science workloads that I was talking about. So if we want to disaggregate memory and we want to do it inside the rack, what do we want to achieve? What are the goals of these designs? We want to satisfy its chips maximum escape bandwidth, just because we don't want to starve a GPU or memory CPU of its bandwidth, because that can easily lead to a lot of performance loss. We want to meet the bit error rate that we have in systems today, that's 10 to the minus 18 or less, and we based on our modeling, forward error correction will do that for us, but we do have to account for the extra latency that gives. We want to minimize energy overhead because, why not? Everybody wants to do that. And also, we want to minimize the latency overhead. And that's something I'm going to come back to that, because actually we noticed that that has a large impact on the performance impact of disaggregation. Now, for the photonics, we wanted to implement this rack using photonic components, but all the components that we have in our model are demonstrated, and some of them are commercialized. So this is something that Xscape is actually showing on the floor. It's available commercially right now, and it's that was that acronym in the title, the Dense Wavelength Division Multiplex Link, where the idea is very simply that you have a comb laser source on the left. It produces a bunch of wavelengths that you can think of them as colors. And then all those go into the transmitter. The transmitter has ring resonators, and each ring resonator captures and encodes information in one of those wavelengths. All that light goes somewhere, the receiver receives and can decode each wavelength individually. Now, this is under development, of course, but we've seen in publications like bandwidths that range from 100 to 2 terabits per second. We want to be a little pessimistic, so we assume 200 gigabits for our study, which ended up being enough. And our collaborators at Columbia are also partly developing some of these comb laser sources. Oh, I had an animation I forgot about. So yeah, the comb laser source provides us multiple frequencies and then the ring modulators. So co-packaged optics in the models that we have here are actually very important in meeting, satisfying each chip's escape bandwidth, just because of the bandwidth density that we can get out of co-packaged optics. So how that looks like is basically, if we, this example on the left only illustrates about HBMs, but we can do the same with other chip types. The idea is that we have an active photonic substrate, and we put chips on them. So in this case, HBM, you notice on the left here, so you have a bunch of stacked HBMs. all of them on an active photonic interposer. You have comb laser sources on the left, shining light and working as we saw on the previous slide. And then we have output fibers exiting and providing that communication bandwidth. And if you have a bunch of these MCMs, as you see on the right, and you put even some switches on it, now you can have, that's how we can construct a node, as you'll see in a couple of slides. And now we can have CPUs, we can have memories, and construct dedicated paths end-to-end between them. Now, our collaborators at Columbia also had this prototype about this photonic transceiver, sort of based on the similar ideas as what I showed before, but this basically we have an interposer. On the interposer, we have a photonic integrated circuit that can do some routing, and we have the electronic integrated circuit, EIC, that is the transceiver in this case. All that is on a PCB, and all that is on an FPGA board, and it made for a really nice demonstration for some of this technology that is actually working. But okay, so these are the photonic components that I was talking about. How does this scale up? Because again, we started with the goal of making a photonically disaggregated rack. So I showed you some of the building blocks. So basically, using those blocks, we can construct MCMs, multi-chip modules. Each MCM has its common laser sources on the left, as I showed you, and then the fibers exiting on the right. We can have multiple of these. For simplicity, we can have only one chip type per MCM. That's not a requirement, but it makes some things simpler. So in this case, we can have an MCM with GPUs, with CPUs, and NVRAM, accelerators, and or other components. So with these building blocks, now if we put a certain number of them, and so if we put a certain number of them, and in the middle put a small switching fabric, like I showed you 2 slides ago, now we can sort of make a blade which can sort of replace what we have as nodes in current systems. So we have MCMs, we have some photonic switching components, low radix, not expensive, not much loss either in there, and now we have a node. And scaling up, we have a bunch of these, and now we have a rack. And how we constructed a rack out of this is by having, on the left, as you can see here, a number of optical switches. Now, because of time, I'm not going to go into detail about that part of the optical switches, but I will say one of our targets here was we did not want to have the control plane and all the overhead with reconfiguring switches. So our design was actually based on wavelength selecting switches, AWGRs in particular, having multiple of them, and a solution, a distributed solution for indirect routing as a way to provide point-to-point bandwidth that can fully satisfy a chip's escape bandwidth. So basically, if a GPU wants to use its full bandwidth to talk to a memory, it can do that, but it will have to distribute its traffic across multiple AWGRs. I can provide more detail if you want. We also have a paper on this. But going back to the latency, because this is actually an important point, we can satisfy the bandwidth, but all these photonic components and the distance now adds latency. I mean, the distance makes sense. We've taken the memory farther away from the GPU, farther away from the CPU, so there's some latency to that. Various talks quoted similar numbers. We assumed here a reach for a rack, so basically the maximum distance between 2 components in the same rack is no more than 4 meters. So we're talking about 15 nanoseconds, or really 15 to 20 nanoseconds propagation delay just because of distance. And then we're adding 10 nanoseconds of serialization delay, assuming 200 gigabits per second. It's a little conservative, but it worked out. And then the forward error correction latency, 2 to 3 nanoseconds. So how we ended up in our model is we assume that the extra latency that this disaggregation hardware adds is 35 nanoseconds. And that's actually important, because now this latency will go in between a CPU and the memory, a GPU and the memory, and some of these hardware components, some applications are less tolerant to extra latency to get to memory. So I'm only going to show you one result slide, but I want to really illustrate the impact of latency in performance. So this graph, we're going to walk through it. I know there's a bunch of colors here and everything, but we're going to walk through it. What this graph compares is how much faster our photonic rack is, disaggregated rack is, versus an equivalent that uses electronic switches instead to also implement the same to also implement inter-rack disaggregation. Now, for short distances, the having copper or light in terms of propagation delay makes a really small difference. So the extra latency in the electronic case is really in the switches. We looked at publications and spec sheets and everything. The fastest switches that we could find for the Anton 3 and the PCIe that were pretty comparable. I think the PCIe Gen 5, if I remember this case, it was 85 nanoseconds. So we use that number. Of course, if something faster comes along, we can just plug it in. But we evaluated the impact of that extra of that latency between CPUs or GPUs and memory in 3 cases. We have in-order CPUs, out-of-order CPUs, and GPUs. And on the x-axis, we have a bunch of benchmarks, suites, and for each one, you get average and maximum. And as you can see, some benchmark suites didn't run on GPUs or vice versa. But the point is, because our disaggregation, our photonically disaggregated rack can provides this disaggregation with 35 nanosecond versus 85 in the electronic case, our rack is actually faster, meaning the applications run faster in our rack compared to the equivalent electronic rack. And you can see the range here is, well, depending, of course, it's like anywhere from 10 to 60%, depending on the application and the characteristics. Of course, there's correlation here with the cache miss rates and so on. I'm not going to go into that. But let's see. Also, yeah, and a couple of smaller notes. The approximately power overhead of that extra hardware that we added, the extra photonic hardware that we added to the rack is about 5%. So small, but measurable. And also, if we want to scale up the performance argument on the system, of course, this is more like an estimate, but in any case, with our rack, we can have a system that has the same compute throughput, but has about 4 times fewer memories and 2 times fewer NICs. I didn't talk about NICs much, but the focus here is memory. So I guess we have 3 minutes, and if anybody has questions.
Hello. What is the connection time for like an optical switch? Because I assume this is not a packet optical switch, but rather circuit.
So we're using parallel AWDGR, so there's no reconfiguration to be made here.
But still, you have to set it off and make a connection, right? Because you still have to, because the receiver CDR still has to log because you're changing wavelengths, right?
So the assumption, well, the design that we're making here is that every source, I mean, the lasers are on. So and every endpoint knows where these wavelengths are leading to. So by knowing the destination, it can choose where to send, and that wavelength is on to begin with. So it just transmits.
Right, but the receiver has to switch, right? No?
Yeah.
So
Yeah, it's an all-to-all.
All the time.
It's listening all the time. That's basically what it means. Yeah.
Thank you.
Thank you for the talk. I have a question about the prefab BR. So what kind of the prefab BR you are targeting here? And what kind of FAC are you going to use? Because I see the latency requirement is pretty tight. Like the KP4 FAC we're familiar with is already like 20, 30, or 50, or if you include everything, it's already close to like 40 nanoseconds.
Yeah, this was some lightweight FEC that I remember the specs. I actually don't. It's FEC light, and those were the numbers they were reporting. John is a co-author, by the way, and he focused on that. So I can get you the reference and the numbers, but that's a good question. We were just going by the specs that they were reporting.
Okay, so it's some optimized FAC that's lighter
Yeah.
than.
Yes.
Oh, okay.
Okay.
Thank you.
Okay, let's thank the speaker.